Every single day, you make a deal with an algorithm invented by a chain-smoking Dutch computer scientist in 1956. You probably made this deal 5 times before breakfast today, when you checked Google Maps this morning, when Instagram decided which stories to show you first, when your Uber found a driver, or even when your Wi-Fi router decided how to send this very video to your screen. They all use the same fundamental algorithm. And here's the thing, this algorithm is so elegant, so beautiful, that you can learn it in the next 20 minutes. By the end of this video, you'll understand the hidden logic that powers billions of decisions every second across the planet. Welcome to the world of Dijkstra's Shortest Path algorithm. I'm going to tell you 3 stories today. First, the story of a brilliant, controversial computer scientist who solved this problem while shopping with his fiancée. Second, how this algorithm actually works, and I promise, it's simpler than you think. And third, the mind-blowing ways it secretly controls your daily life. But before we dive in, let me blow your mind with something. The device you're watching this on, it's running Dijkstra's algorithm right now, multiple times per second. See, the internet doesn't have a straight line from my uploaded video to your screen. It has to find the fastest path through millions of possible routes. And it does this using, you guessed it, Dijkstra's algorithm. The year is 1956, Amsterdam. A 26-year-old programmer named Edsger Dijkstra is sitting in a cafe with his fiancée. While she's shopping, he's thinking about a problem that's been bugging him. He works at the mathematical center, and they've just built one of the first computers in the Netherlands, the ARMAC. They want to show off this million guilder machine at an open house, but they need something visual, something impressive that normal people can understand. The demo they've planned? Type in any 2 Dutch cities and the computer will find the shortest route between them? Remember, this is 1956. There was no GPS, no Google Maps. Finding the optimal route between cities is something humans do with paper maps and lots of guesswork. But here's the problem. How do you teach a machine to find the shortest path? Sitting in that Amsterdam cafe, Dijkstra had an epiphany. He grabbed a pen and started sketching on a napkin. In 20 minutes, without any paper, without any computer, he solved one of the fundamental problems in computer science. What's crazy is that Dijkstra didn't even publish this algorithm for another 3 years. He thought it was too simple, too obvious. He literally said, "One morning I designed the algorithm for the shortest path. It was a 20-minute invention. In fact, it was published 3 years later. The publication is still readable. It is, in fact, quite nice. And one of the reasons that it is so nice was that I designed it without pencil and paper." This 20-minute invention would go on to become one of the most important algorithms in human history. And I'm going to teach it to you the same way Dijkstra thought about it. Simple and visual. Imagine you're at a party and there's a rumor spreading. You're the source of the rumor. Don't worry, it's a good rumor. Like where the secret stash of good snacks is hidden. Each person at the party is a node in our network. Some people are standing close to each other, some are far apart. The distance between people represents the cost or weight of sharing information between them. Here's Dijkstra's genius insight. The rumor spreads like a wave, always reaching the closest people first. You, the starting point, know the rumor with certainty. Your distance to yourself is 0. Everyone else, they haven't heard it yet. Their distance is infinity. Here's our network of 6 people connected by different paths. Each connection has a weight representing the time it takes for information to travel between them. We have you, Alice, Bob, Carol, Dave, and Eve, all connected through various routes with different travel times. The numbers show how long it takes to reach each person directly. For example, reaching Alice takes about 4 time units, while Bob only takes 2. We can start by setting your distance to yourself as 0, because you're the source. Everyone else starts at infinity, meaning we haven't found a path to them yet. Now let's run Dijkstra's algorithm to find the shortest paths to everyone. We begin with you, the starting point. Now let's run Dijkstra's algorithm to find the shortest paths to everyone. Now check all your direct connections. First, Alice, it takes 4 time units to reach her. Update Alice's distance to 4. And next, check Bob. It takes about 2 time units to reach him directly. You want to update his distance to 2, and this is his current best path. Now, among the unvisited nodes, Bob has the smallest distance, and that is 2. Select Bob as our next node to process. From Bob, we can reach Carol, and the total distance would be 2 plus 3 equals 5. And you want to update Carol's distance to 5, and this is her first known path. Now Alice has this next smallest distance. From Alice, we can also reach Carol, and the total distance would be 4 plus 1 equals 5. This equals Carol's current distance of 5, and so no update needed. We have a tie. We have 2 equally good paths. Now Alice can also reach Dave. The total distance would be 4 plus 3, and that equals 7. At this moment, Carol has the smallest remaining distance, and that will be 5, and so you'll want to select Carol for processing. Once we've marked Carol as visited, her optimal path is now confirmed. From Carol, we can then reach Dave, and the total distance would be 5 plus 1 equals 6. This is better than Dave's current distance of 7. So we want to update Dave's distance to 6. We found a shorter path. Now Dave has the smallest remaining distance, and that will be 6. And so we'll want to select Dave for processing. We want to mark Dave as visited, and his optimal path is confirmed. And so from Dave, we can reach Eve, and the total distance would be 6 plus 2, and that equals 8. And so we want to update Eve's distance to 8, and this is her first and only path. Finally, Eve is the only unvisited node, and we want to select Eve for processing. And so we'll mark Eve as visited, and all nodes at this point in time have been processed. And so here are the shortest paths from you to everyone else. The golden line shows the optimal routes Dijkstra's algorithm discovered. So 4 time units to Alice directly, and for Bob we have 2 time units directly. For Carol we have 5 time units through Bob, and for Dave we have 6 time units through Bob, then Carol, and for Eve we have 8 time units through the complete chain. And so this is how Dijkstra's algorithm systematically finds the shortest paths from any starting point to all other destinations in a weighted graph. Every time you load a website, your request doesn't travel in a straight line. It hops through multiple routers, each one running Dijkstra's algorithm to figure out the fastest path to YouTube's servers. But here's the twist. Shortest doesn't mean physical distance. The algorithm weighs network congestion. Heavy traffic equals longer quote-unquote distance. Connection speed. Fiber optic equals shorter quote-unquote distance. Failed connections. Broken cable equals infinite distance. Your router runs this calculation thousands of times per second, constantly finding new optimal paths as network conditions change. When LinkedIn shows you second-degree connections or Facebook suggests friends, They're using modified versions of Dijkstra's algorithm, except instead of finding the shortest physical path, they're finding the shortest social path. The distance between people might be how often you interact, mutual friends, similar interests, geographic proximity. Instagram's algorithm deciding which stories to show first, it's calculating the shortest path to content you'll engage with, where distance is the inverse of predicted engagement. Every enemy chasing you in a video game, every unit you command in a strategy game, they're all running Dijkstra's algorithm or its variants. In Civilization, when you tell a unit to move across the map, it's calculating terrain costs, mountains equals high cost and roads equals low cost, enemy territories, infinite cost if you're not at war. Dangerous areas, higher costs near enemy units. The pathfinding runs so fast you don't even notice it, but it's there, calculating millions of paths per second. Google Maps isn't just running Dijkstra's on a simple network. It's considering current traffic from millions of Android phones, historical traffic patterns, rush hour on Tuesdays for instance, road closures and construction, traffic lights and stop signs, your personal preferences, avoid highways, avoid tolls, and it's not just running it once. It's constantly recalculating as conditions change. Miss a turn, Dijkstra's algorithm instantly finds you a new optimal route. When you search for flights, airline systems use Dijkstra's to find routes, but shortest might mean cheapest price, shortest travel time, fewest connections, best airlines. The algorithm runs the same way, just with different definitions of quote-unquote distance. Dijkstra's algorithm is used in epidemic modeling, finding how distance spread through populations, DNA sequencing, finding optimal alignment paths, and drug discovery. High-frequency trading systems use Dijkstra's to find the most profitable paths through currency exchanges, buy USD, convert to Euro, then to British Pound, back to USD. If you find the right path, you profit from tiny differences in exchange rates. The algorithm runs millions of times per second, finding profitable cycles in the global financial network. But Dijkstra's algorithm isn't perfect. It has some crucial limitations. Limitation 1, if your graph has negative edge weights, imagine roads that make you go back in time, Dijkstra's breaks. You need the Bellman-Ford algorithm instead. Limitation 2, all or nothing. Dijkstra's finds the shortest path from one source to all other nodes. If you just want the path between two specific points, A-star algorithm is often faster because it uses heuristics to guide the search. Limitation 3, static networks. The basic algorithm assumes the network doesn't change while it's running. For dynamic networks, you need variants like D-star, dynamic Dijkstra's. And so this spawned a whole family of algorithms. We have the A-star, which uses heuristics for faster pathfinding in games. The Bellman-Ford, which handles negative weights. We have the Floyd-Warshall, that finds the shortest paths between all pairs of nodes. And last but not least, the Johnson's algorithm, which combines Dijkstra's and Bellman-Ford for efficiency. Thank you for joining me on this journey through the algorithm that secretly runs your life. If you enjoyed this deep dive, don't forget to hit like, subscribe, and comment on what you'd like to see in our next video. Until then, may all your paths be optimal. I'll see you in the next one.